Okay, so in the last lecture, we first finished the remaining part of the last lecture. Okay, so the remaining part of the last lecture. So in the last lecture, we have covered the early or late selection debate, and then NICE suggests that perhaps we should not frame the question as early or late, but rather we may want to list the features that are processed with or without attention. Then, following the license approach, we have Trisman proposed the feature integration theory, which explain what kind of visual processing may require attention and which kind may not. Then, guided search theory proposed that pre-attentive information may be used to guide the allocation of attention, so that we may want to allocate our attention to different places, not in a random fashion, but we will gather the bottom-up and top-down information in order to very intelligently decide where to put our attention to. So in the last lecture, we have finished with the guided search model. So now we will continue with the load theory. What the load theory talks about? It talks about selectivity. So what is selectivity? Selectivity refers to how well we can select the relevant input and how well we can avoid the distraction. Okay? So remember, in the very first line of the last lecture, we said concentration refers to how well we can avoid distraction. So the concept is similar. So if you compare the broadband filter theory with Trisman's attenuation theory, they are both early selection accounts, right? They both select on the basis of simple physical features, right? The only difference between the filter theory and the attenuation theory is, according to filter theory, for those inputs that you do not select, you will not process them at all. But for the attenuation theory, you only reduce those inputs, but you still somehow process those inputs, right? Now, this theory generally ignores the issue of selectivity. But if you compare the filter theory and the attenuation theory, you are actually talking about different degree of selectivity, right? For filter theory, it actually assumes a perfect selectivity. So if you want to select this input, you really do not process that input at all, right? So it actually is, to some extent, it's good, right? Because it's like when you want to focus on something, you really will not get distracted by other things. So this would be perfect selectivity. For attenuation theory, it says even I do not select an input, I will still somehow process it. But it does not specify, it does not describe how much I may process the unselected input. Okay, we say we'll still process that a little bit, but how much is a little bit? So they generally ignore this issue. The load theory today want to describe what factors may affect our level of selectivity. Okay, will there be some factors that influence us so that sometimes we can select better and ignore better, or sometimes we may select less effectively and we may process the distraction more? So imagine when you want to prepare for your exam, and then you want to ignore your very noisy little brother in the living room. Okay. Now, two scenarios. One is that, well, you have very good sleep and you have very good rest, and then you have all the very good mental state to start your exam. So this is the scenario A. For scenario B, well, you have not slept for many days already, and you are very tired. Okay, and then you go to still study for the exam. Do you think which scenario you can concentrate better? Of course, it's the first one, right? In first one, you have the energy to concentrate, right? Then probably even your brother is shouting outside, you can still, to some extent, maintain your concentration. Okay. However, if you haven't slept for 2 days and you still have to revise, then probably you will very much get distracted by other noise. So this example is saying that there are some factors, for example, how energetic you are or how tired you are, may affect your level of selectivity. Okay, when selectivity is good, you can avoid distraction. When selectivity is bad, you will process the distractors. Okay, so in other words, we want to look at what factors may affect the level of selectivity today. So the load theory suggests that at least two issues will influence the level of selectivity. It focuses on our current attentional or mental demands. So the load theory focuses on two types of load. The first type of load is perceptual load. We will improve selectivity. The second kind of load is cognitive load. We will reduce selectivity. So I will not explain it here because we will explain them one by one. So first, what is perceptual load? Perceptual load refers to if you have a visual task or if you have a perceptual task, how difficult it is for you to work on it. Okay, if I give you a very, very small letter to identify, then you have to focus very much in order to identify. So that would be a very high perceptual load. Okay, very difficult to see. So Levy, 1995, studied the effects of perceptual load. So now let us first look at Levy's experiment and to first to see how she manipulates perceptual load. Okay, we'll go to other details very soon. So here, the task was to discern the target. Is it an X or a Z? The target only lies on the central row. Okay, the others are irrelevant. Okay, the letters only lies on the central row. So the task was very simple to judge whether it is an X or a Z. And then probably you press a key. Okay, so this is a Z, you press a key. This is an X, you press another key. Okay, now in the left conditions, it is quite clear that it is not difficult to do. You just identify the letter. But on the right condition, it is more difficult to identify the target, right? Because you have some other letters surrounding it. And you really need to focus on the target in order to discern whether it is a X or it is a Z. Okay, so in other words, it is perceptually more difficult, perceptually more demanding, more difficult to see. So this difference, okay, marks the manipulation of perceptual load. Okay, in the left, more easy condition, it have a low perceptual load. In the right, more difficult condition, it have a higher perceptual load. Okay, but the task is similar. Then, with this manipulation, Levy want to study selectivity, how well a person can select. How can Levy study selectivity? If we say selectivity is about how much we process a distractor, then we can study the influence caused by a distractor. So why don't we just put a distractor on the screen? So this one, and this one are the distractors. Okay, so the experiment will study what influence is given by the distractor. So there are three types of distractors. Okay. Very good. So there are three types of distractors. One is incompatible. So the target in this example is Z, right? And then the distractor in this example is X. X actually possesses a task relevant identity, isn't it? Because your target could either be X or Z. If the distractor is X, okay, it contains a task relevant feature, right? A task relevant response. Therefore, this distractor is incompatible to the target. If you ever process this distractor, it may probably lead to poor performance because you will be confused, right? Should I say Z and press that key, or should I say X and press that key? That is actually a little bit distracting. Okay. Another type of distractor is neutral. So it's a P, it's not a target, right? However, P does not associate with any task relevant response. It is not an X, nor it is a Z. So it's probably not going to interfere with you so much. Okay. The third type of distractor is the compatible distractor. So in this example, it is a Z. But in this example, the target was also a Z. Therefore, if you ever process the distractor, not only it does not interfere with you, but possibly it may even help you, right? Therefore, it's called a compatible distractor. So you can imagine, if you have perfect selectivity and you do not process the distractor, will the distractor still produce any effect? Okay. If you have perfect selectivity, and then that means you can avoid the distractor at all, then will the distractor produce any effect? No, right? Then will there be any difference between these three conditions? No, there will be no difference. However, if you do not have perfect selectivity, if you have a poor selectivity, then what you will do, you will process the distractor. If you process a distractor, what do you expect? You will have poor performance for incompatible, intermediate performance for neutral, and then you will have a better performance for the compatible condition. Okay? So now we want to know whether we will have a large compatibility effect in the low perceptual low condition or high perceptual low condition. Okay? Which condition will have a better selectivity? Okay, good question. And this is the results. Now, again, let's first learn to read the graph. The y-axis was mean target identification time. That means response time, right? For response time, the slower the poor. And then what conditions we have in the x-axis? Neutral and incompatible. So theoretically, okay, if you have perfect selectivity, they should be the same. And theoretically, if you have poor selectivity, then possibly you will have poor performance in the incompatible condition. Okay, so this one will be higher because it's slow. Now, where is our conditions? High perceptual load versus low perceptual load. And what is our results? This is quite clear. In the high perceptual load condition, do we have good or bad selectivity? Good, very good, perfect selectivity even. And what about low perceptual load condition? We have better or poorer selectivity? We have poorer selectivity. So take them together, the conclusion is we have better selectivity with a higher perceptual load. Okay? Now, can you make a guess on why does it happen? Why a higher perceptual load will produce better selectivity? Can you make a guess? Right. The task is more difficult, and therefore, you need to focus your attention really to the task. Okay? Then the more you try to focus, the better selectivity you have. So second, okay, in 2004, the same group of researchers have done another experiment to look at another type of load, okay, which is cognitive load. So cognitive load refers to whether your mind is occupied by something. Okay, if you keep thinking about something, okay, you have a high cognitive load. Now, when you are thinking about something, you have a high cognitive load. Do you guess you have a better or worse selectivity? Probably worse, right? Now, we will take a look at the results to see whether it's actually true. How do you manipulate cognitive load? There are many ways, right? I can ask you to do calculation in your mind, right? Or I can ask you to think about something, right? And one very good way to manipulate cognitive load is to use memory load. Ask you to remember something, okay? So during the course of memory retention, I will do the same task as the 1995 experiment, okay? So there are two conditions. One is low memory load condition, therefore low cognitive load condition. So the task is easy. You remember the number, okay, and then you do the same task, and then after that you will see a test. Is the number you remember a 4, and then you say yes or no, okay? So for the high memory load condition, what do you have? You have 6 numbers to remember. Okay, you have 6 numbers to remember. But you still do the same task, and then you see the test. In the test, you have to answer among the number you try to remember, is that a 4? Okay? So this is the manipulation of memory load. And then in the same time, in the middle task, Levy tried to replicate their original experiment. Okay, so in this slide, in this example, you have a high perceptual load condition, isn't it? But in the actual experiment, you also have a low perceptual load condition. Okay, therefore, you have a high memory low, high perceptual load condition, high memory low, low perceptual load condition, and low memory low, high perceptual load condition, and then low memory low and low perceptual load condition. Okay, so you have all 4. So therefore, you can study the effect of perceptual load and cognitive load in this experiment. Now, as a revision, let us first look at the effect for perceptual load. Okay. First, what is the y-axis is still response time. Okay. And then what conditions we have? We have a low perceptual load versus a high perceptual load condition. We also have the low working memory load and high working memory load condition. Okay, and then to measure the selectivity, we will compare the incompatible versus compatible condition. If selectivity is good, we will have more similar or more different performance for the incompatible and compatible condition. More similar or more different? Right, more similar. Okay, so let us take a look. So first, let us ignore the working memory part and focus on the perceptual part first. Okay, then we go to the working memory. So for low perceptual condition, what do we have? So because we want to ignore the working memory load first, let us look at that very, very roughly. Okay? So for the low perceptual incompatible condition, you have the performance around here. For the compatible condition of low perceptual load, you have performance around here. So how large a compatibility effect do you have? About this large, right? Then what about the high perceptual load condition? So again, very, very roughly, incompatible around here, compatible around here. So basically, you do not have a very large compatibility effect. Okay. So we do not need to be very exact, but just to take a look at it, is it a similar result as the last experiment? Is it similar? Yes, it is similar. Because for low perceptual condition, we have a larger compatibility effect. Remember here, for the low perceptual condition, we have a larger compatibility effect. On the other hand, for the high perceptual condition, we have a smaller compatibility effect, which is the same as the 1995 experiment. So is it a successful application? Yes. Okay. Okay, therefore, for the perceptual low part, the result is same as the V. A higher perceptual low will reduce compatibility effect and it increase selectivity. Okay, if we make a guess on why was it the case, then we say it's because when the perceptual low is high, the task is hard. Then you try to focus, then you avoid the distraction better. Then what about cognitive low? Let's just take a look. Now, first, the black bars. Now, let's just first focus on the low perceptual low side first, and then we'll go to the high perceptual low because we will look at this twice. So, for the low working memory low condition, okay, the compatibility effect is this large, okay. When you compare immutable to compatible for the low working memory low is this large. What about high working memory low? So it's around here, right? And the other bars here. So this is the compatibility effect. Which one is larger? The high-low condition is larger, right? The high working memory low condition is larger. I should use blue. Okay, blue. Okay, very good. Okay. Now, on the other hand, for the high perceptual condition, okay, so basically, for low working memory low, you basically do not have much effects. Okay. And then for the high working memory low condition, you still have some effects. Okay, you still have some effects. So what is the overall picture? Okay, whether perceptual low is high or not, when working memory low is lower, then you have a smaller compatibility effect. And whichever perceptual low condition you are in, for the high working memory low condition, you have actually a larger compatibility effect. Okay, do you follow? Shall I say it again? Yeah? Okay. Now, this time we want to focus on the working memory low, right? However, we have the low and high perceptual low plot into two sides. So we'll look at that one by one. Okay. So first, we'll look at the left panel for the low perceptual low. Now, we want to compare the high and low working memory low, right? So for the low working memory low condition, the compatibility effect is this large. Okay. And for the high working memory low condition, the compatibility effect is this large. Okay. Therefore, in high or low working memory low condition, is the compatibility effect larger? High, right? High. Okay. So what about in the right panel? What about for the right two bars? Okay. Then we do it again. For the low working memory low condition, basically the compatibility effect is very close to zero, slightly negative, so very close to zero. For the high working memory low condition, you still have some compatibility effect. Okay, so when you compare between high and low working memory low condition, which one have a larger compatibility effect? Which one? High. So is it the same for the two? Yes, they're the same. So the big picture is the same. High working memory load condition is associated with a larger compatibility effect. Okay? So from this graph, you can see the two different kind of load effects is adding together. But then we can still separate them and to look at each one. Okay? Now, for the cognitive load manipulation in terms of working memory load, a higher load will increase the compatibility effects, which means a poor selectivity. Okay, so is it in line with our expectation? Is it in line with our expectation? Yes, it is similar to our expectation. We are saying if we are thinking about things, okay, then we feel occupied mentally. Then can we still concentrate? We no longer, we will concentrate much poorer. So therefore, to say the explanation again, so whenever we do a task, we want to focus on our task. And that means we want to ignore our distractor. When our perceptual load is high, that means the task is perceptually hard. We know that we put more attention to process the target, and therefore the distractor is processed less. That means a better selectivity. However, when cognitive load is high, that means we are cognitively occupied. Okay, maybe we are thinking about something, maybe with some personal matters. Okay, exploring myself, or maybe we are doing a mental calculation, or maybe we are trying to remember a phone number, and so on. We are cognitively occupied. When we are cognitively occupied, it is more difficult to concentrate. Then you are more easily distracted. Okay, so this is the idea of the load theory, which describes the factors that influence how well can we select. Okay. So, in the last lecture, we have been talking about the issue of attention in a general, in very general fashion. Okay, so sometimes we talk about auditory attention, and sometimes we talk about visual attention. So we talk about attention in general. But then after 1980s, after Chisholm had proposed the feature integration theory, there is much more research on visual attention than auditory attention. Therefore, it becomes a important focus of research. Therefore, today we will focus mainly on visual attention. When we talk about visual attention, of course we use our eyes. If I say focus on the clock, then you use your eyes to look at the clock, right? So when we visually attend to a location, very usually we will use our eyes to look at that location. This is one way to use our attention, right? By using eye movement. Okay. In this situation, we call it overt attention. Okay. Overt means explicit. We really move our eyes there. Okay. However, when they ask, if I keep my eyes still, if I do not move my eyes, can I still, okay, without moving my eyes, attend to, let's say, the left, or attend to the right, or attend to the top? Can I still do that without moving the eyes? That is not trivial, isn't it? So you need some study to figure out whether we can attend without moving our eyes. And to tell you first, actually we can attend without moving our eyes. Okay? Okay? We can actually attend without moving our eyes. Okay? So if we attend without moving our eyes, then this is called covert attention. Covert just means implicit. Okay, so you are not really moving your eyes, but you are attending, okay, to different places in the visual space. 咁啊，個概念就好似我哋平時所講射呢眼咁樣嚇。如果我想睇下嗰邊嗰個人， okay， 但係我又唔好意思俾佢知喎，咁我就通常就我個頭就唔擰過去啦，但係我隻眼就望過去啦，咁我哋就叫射呢眼啦，係咪？咁變咗 covert attention 咧，可以話係再高一個層次，就係你連隻眼都唔望佢，但係你將注意力擺喺佢嗰度。OK， 咁呢個射呢 attention 咧就係 covert attention 啦。Now, how do we know whether we can attend without moving our eyes? Well, first of all, of course, we can attend via moving our eyes. I think this is quite trivial. We do not need a lot of experiment to show this point, right? But how do we know if we can still attend without moving our eyes? Well, what we can do is, okay, do an attention experiment, measure the attentional benefit, but we stop the person from moving their eyes. Is the benefit still there? Okay, if that person do not move their eyes, but I do an attentional experiment and measure the attentional benefit. If the benefit is there, that means you can actually attend without eye movement, without actually moving your eyes. Okay, so Posner did that in 1950s. So this is a very simple visual attention experiment, okay, invented by Posner. This is so-called a Posner task, named after him. So here we have three types of cues. Okay, this cross is a neutral cue because this cue does not tell you where the target is going to be. Therefore, this cue is uninformative. Okay, it's useless for you. So after this cue, you only focus on the middle, and then the target may occur in either side. When you see the target, you press the key as quickly as possible. Okay. The second kind is a valid cue. So this is an arrow pointing to one of the direction. If the target actually occur, okay, at the right place, this is called valid. The cue is valid because it actually predicts the target location. Okay, so in 80% of the time. Okay, so it's really predict the location 80% of the time. So you will expect that performance to be better, right? Because the target occur at the expected location. Your attention is already there. In the third kind of cue, okay, the cue pointing here, well, because the cue is 80% correct, where will your attention go? Your attention will, of course, go here. But, well, unexpectedly, the target actually occurred here. Okay, this is why it's called the invalid condition, constituting 20% of the trials. Will the performance good or bad? Probably worse, because you expect it to be here, but it actually occurs here. Then your response lower. Okay. Now you can well imagine that if you use your eyes, if you move your eyes, then that means following this arrow, you move your eyes here. Okay. Then when the target actually occurs here, okay, then you will need to move your eyes from here to here. Then you will see an attentional cost, right? On the other hand, if the eye actually is here, then you do not need to move your eyes, then you save some time, so it's an attentional benefit. Okay, so this is no surprise. For overt attention, okay, eye movement will generate an attentional benefit. The question is, now I want to see whether without moving our eyes, you'll still get the same effect. Therefore, the instruction is, okay, your eyes need to keep in the middle. Your eyes need to keep in the middle and in the middle. Never move your eyes. Okay, it's difficult, but try to keep your eyes in the middle. Okay, then you do the same task. The question is, how do you know if the participant actually do not move their eyes? Then you can use some machine to monitor their eye movement, and that's called the EOG. What is EOG? EOG comes along with every EEG machine. Okay, for EEG, it measures your brain wave, right? And nearly all EEG machine will come with some electrodes that is made for you to stick near the eyes. Then whenever you move your eyes, it receives some signal. Okay, then the experimenter will know when have you moved your eyes. If you move your eyes during a trial, you do not analyze the trial. Okay, then for the remaining part, the participant really followed the instruction and the eye is not moved. In those cases, the eyes, we are sure that the eyes is not moved. Then we will still give the attentional effect. If yes, then we know that attention would work even you keep your eyes still. Okay? So therefore, this is a detection task. You press the key as quickly as possible when you see the target. The cue was 80% accurate, so you have every reason to follow the cue. Now, you cannot move your eyes. Do you still have any attentional benefit? And actually, you have. Okay, so here, y-axis is response time, x-axis is the validity conditions. Okay, so in valid condition, neutral condition, and valid condition. If attention have an effect, valid condition will be the quickest, and the invalid condition will be the slowest, right? So as you can see, even you do not move your eyes, so you will not take extra time to move your eyes from the expected location to the unexpected location for the invalid condition, right? However, do it take time to move your covert attention? Okay, that's the question. Now, it seems that it does, okay? So, for the invalid condition, it is slowest. For the neutral condition, it is in the middle. And then for the valid condition, it is the quickest. Okay, so this is a pure attentional effect. Okay, pure attentional effect, no eye movement. Okay. So this shows you evidence for covert attention. Now, what is this tool? You may ask. Is actually irrelevant to us. Well, in Posner's paper, he did not only do this task, but he also do some other tasks. For example, to judge what letters is shown here. Okay, and then so here you have a choice spatial or choice symbolic. It's actually some other task, but the logic is the same, and therefore you can see the effect is very similar. Okay. So Posner's experiment gives us evidence for pure covert attentional effect. Of course, we can allocate our attention by using our eyes, but we can also move our attention independent of eye movement. Okay? In Posner's experiment, it also gives us evidence for goal-directed allocation of attention. What does it mean? It means that we can, okay, if we know the cue is useful, okay, we can, out of our own will, decide to move our attention to a certain location. So this is goal-directed attention. In this experiment, this arrow do not automatically move our attention, isn't it? We move our attention here only because we know that this arrow means we should attend to the left, and we know the fact that this arrow is very likely to be useful. Therefore, we decide out of our own will to move our attention here, right? So this is a so-called goal-directed location. And this is similar to the case when we want to cross a one-way road. Okay, and usually there is a sign to tell us which direction to look for traffic. Okay, so when we look at this sign, okay, it is from our own view, we understand the meaning of these words, and we understand the meaning of this arrow, and this is why we decide for ourselves to look for that direction. Okay. So this is what we call goal-directed attentional control. We control our attention due to our goal. Okay? So we have many names for this idea. Either we can say it's a goal-directed attentional control, or we can say it is endogenous attention, voluntary attention, or top-down attention. These concepts are very similar. They are slightly different, but for our purpose, okay, they are largely the same. Okay, for our purpose, they are very similar. But actually, there is some very minor differences between them, which we are not going to talk about. So on the other hand, okay, in other cases, visual attention is not allocated out of our will. Sometimes when we are waiting for a traffic lamp and to cross the road, okay, we look at the opposite side, okay, and there is something special, okay, we usually will not pay a lot of attention there. However, if you see someone is waving over there, oh, it's your friend. Your friend see you first, and therefore your friend waves at you. Will you notice your friend? Yes. Okay. That friend is waving at you, very big movement, so you notice your friend. Okay. However, your friend noticed you first. Before you see the wave, you do not know your friend is there. Therefore, originally, you have no reason to look at that location. Right? Originally, you have no reason to look at that direction. But because of the waving movement, okay, your attention is attracted there. Only after your attention is there, you know why you should look there, right? Therefore, it is not goal-directed attention. This is stimulus-driven attention. You allocate your attention to that direction because of the stimulus. The waving movement is very eye-catching. Therefore, you look there. So your attention is driven by the stimulus. Okay, so it's called stimulus-driven attentional control. Okay, so it's the same idea as some warning signs. For example, the fire alarm. Okay, when it flashes, you are attracted by it and you look there. Okay, or the alarm sound. Okay, when it rings, it's so loud, so you know you should look somewhere. Okay, so this is some. This is a way to control our attention in a stimulus-driven fashion, not out of our will, but it's due to some very salient, very strong stimulus. Okay. So similarly, we have other names. Somebody call it exogenous attention, involuntary attention, and bottom-up attentional control. So there are some slight difference between them, but for our purpose, they are very similar. Okay. So we'll look at two experiments that give us evidence for stimulus-driven attention. Okay? If we have no reason to attend to a certain location, but perhaps there are some very eye-catching stimulus there. Okay? Will my attention be attracted there so that it will produce some attentional benefit? Okay? This is the question. So Yankees engineers carried out such an experiment. So let us look at it. So it studied stimulus-driven attention by stimulus onset. In other words, if a new object come out from the blue, come out from nothing, okay, if a object suddenly occurs, okay, then we will attract your attention. So let us look at the experiment. So the task was to see whether a target P is there. Okay. If it is there, okay, you press the key. So originally, you have some placeholders here, very similar to the display of some old-style calculator. Okay, the old-style calculator. Okay. And then some of the strikes on the calculator, on the letter will goes away, okay, until a letter is shown. Okay. So let me write again. Sorry. Oh, what is okay. 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 So let me write again. So it is like calculator digit. Okay. And then let's say it's a U. Okay. Then these two stripes disappears, and then it becomes a U. Okay, so you get it. Okay, so why do you have these placeholders? This is because they want to compare new objects with old objects. Okay, so these are old objects because they are already there. So when the new occurs, there is no new object suddenly coming out. Okay, so for these 1, 2, and 3 places, there is no object suddenly coming out. However, for this location, this P is actually a new object. Okay, this P is actually a new object. So common sense tells us that if there is suddenly a new object, it's probably very eye-catching, right? So they want to study the effect of this feature. Oh, sorry. No comment. Anyway, so this one and this one are new objects. Okay, are new objects. Okay. So in the left condition, the target happens to be a new object. In other words, the target happens to possess the stimulus onset feature. Okay. On the right-hand side, it is a so-called non-onset target. That means the target is not a new object. Okay. Now, what would you expect if the onset feature, if the new object feature, somehow attract your attention? You expect that it is better to detect a onset target. It will become faster, right? And also is also more efficient. Okay. Now, what do I mean by efficient? It means, okay, if this is eye-catching, I study this target, this item first, and then I know it's a target. If I study it first, will the number of other items matters? No, because it's always the first one, right? So no matter, okay, there are other, more other items or less other items, okay, so it's still the same time. However, if onset target do not have any special priority, okay, then we just look at them one by one. Is it a P? No. Is it a P? No. Is it a P? Yes. Okay. Then what do you expect? You expect a serial performance, right? The more items, the slower. Okay. So this is the difference. Now, the next question is it an experiment that look at goal-directed attention? No, it's because among these 4 objects, the target will occur at each of the 4 locations by chance. Therefore, there is no real reason to prefer to look at the onset or the others location. Okay, is there any benefit or cost to look at the onset location? No. Okay, they all have 1 in 4th chance. Okay, so if there are any priority given to the onset target, That would mean a stimulus-driven benefit. Okay. So let's look at the results. Okay. So the y-axis is response time, and then the x-axis is the number of items or display size. In the last slide, the example is 4 letters. Okay, but actually they also do a 2-letter condition to look at how parallel or how serial is the task. Okay, so what is the result? Of course, when there is no target, it is the slowest, and also it is the least efficient. That means it is most serial. Why? Because if there is no target, you have to visit all of the items one by one until you will give up, right? So of course, the more item you have, the more item you need to visit, the slower. Okay? And then, what is most important to us is the difference between no onset target and onset target. Now here we can clearly see that the onset target is faster, right? That would probably means that if the target happens to be a new object, okay, even though it is 1 in 4 chance, there is no particular reason to attend to it, it still seems that we will attend to the onset item first. So if it happens to be the target, we will detect it first. So it's become faster, and also it is not dependent on the number of items. Okay, no matter you have 2 items in total or you have 4 items in total, perhaps because it's eye-catching, you will go to this item first. If it happens to be a target, it will get detected immediately. Therefore, response time independent of response time of number of items, right? What about the non-onset target? The non-onset target is nothing special, and so and also there are other you have a number of non-onset items here as well, so you have to look at them one by one, and therefore the response time is slower and is less efficient. Okay. Therefore, the result shows that you have more efficient search with onset target, providing evidence for us to believe that attention is prioritized to onset objects. Because the onset object is nothing more likely than the non-onset target to be the target, we have no real reason, no top-down reason to attend to the onset feature. It's just the same as others. Why do we have to attend to it first? The only reason is, well, it just happens to be eye-catching. Okay? So it's a evidence for stimulus-driven attention. Okay? Now, in addition to onset, there are many other features that may attract your attention in a stimulus-driven fashion. Just now, in the hand waving from your friend example, waving itself, the small movement, is another feature that will grab your attention, right? In another experiment, Tafers used another method to demonstrate that search priority, the order you search, is influenced by bottom-up stimulus saliency. So let's just look at what this experiment is about. So let's first focus on the left part. Okay, we'll talk about the right part after that. So let's first look at the task. The task was to look for a shaped target. So this target have a different shape, right? Just have a different shape. So these are the other items. You need to find out the target, and then you respond to the central line. Is it a vertical or horizontal? Okay, and then you press a key for vertical, or you press another key for horizontal, and then the response time is analyzed. It happens that there might be a distractor that have a different color. Is it eye-catching? Yeah, it's quite eye-catching. Well, your task is to look for a shape. Can you ignore other variations such as color? If you can ignore color completely, well, the color distractor should not matter you. Then you will just go directly to the target. The target is not difficult to find, right? So you should go to the target. However, if this very special color attracts your attention, then you may first go to the distractor, and then after that you realize that, well, it's not the distractor, I'm looking for a shape, not color. Then you go to the shape target again, then you will have a slower response time, right? So will you get slower? So let's just look at the data here. So for the low distractor condition, all the items are green circles, no red circles, okay? So of course this is the easiest, so it's fastest. The more important condition is when you have a color distractor, what will happen? Well, it happens that the color distractor condition is slower, right? It's slower than the low distractor condition. What does it mean? It means that, well, sometimes you will go to the color distractor and then you regret and then you go back to the target, right? So this difference gives you the evidence that attention is captured or is attracted by the salient distractor. Okay? Then you may ask, what is this shape distractor? What is it? Okay? This shape distractor means okay, you actually do not have this red distractor, but then you have another shape distractor, which is in green. Okay, so you get what I mean. Or I cross it out. Okay, I cross it out. You do not have this one, and then you have a shape distractor. Okay, you have a shape distractor. Now, its shape distractor should cause most distraction because it is difficult to distinguish between the target and distractor. So the distractor will very effectively attract your attention, right? So this is for comparison purpose. This is for comparison. Okay, so it has to be slow because it's confused you so much. Okay, so it's for comparison. Okay, so this part, okay, should be okay. So it shows you evidence that attention is attracted by the red distractor or the color distractor. Now, what about color target? Okay, in the right hand side, what is it? In the right hand side, the target becomes a color target. Okay. Okay, becomes a color target. So what does it mean? It means that the target now is a red circle. Okay. Okay. And then what distractor would you have? You may have no distractor, or you may have color distractor as shown now. Okay, or you may have a shape distractor like this. Okay, so it is a shape distractor. Okay, so you have no distractor, shape distractor, or you can have color distractor. Okay, so it is similar to the shape target condition, isn't it? It's just reversing, swapping color with shape. Okay, now originally you look for shape, now you look for color. Originally the color is a distractor, now the shape is a distractor. Okay, so you just swap the role of the two features, right? So theoretically, what would you expect? You probably expect you will get the same effect, right? Because you just swap the role. But the experiment is very similar, so you may expect the same effect. But do you have the same effect? No distractor, of course, is fastest. Color distractor, that means the same feature, Well, of course, it's lowest. Okay, no surprise. But what is more interesting is the shake distractor condition. Does it give a distractor effect? Seems no distractor effect, right? Now, this is an important finding. Okay? Why shape distractor does not give you a distractor effect? We may only explain it this way. Okay? Search priority is based on stimulus saliency. Okay? When a color distractor will disturb a shape target, that reflects that the color distractor is stronger than the shape target. Okay? It is more eye-catching than the shape target. So when you're looking for a shape, you have a very strong color distractor, you go there first, and then you go to the target. That's why you have a slowdown, right? However, when you look for a color target, the color already is a very strong stimulus. Okay, then when you look at it first, you probably still look at it first. Okay, so you look at it first. So does it matter if you have a weaker distractor in the same screen? Okay. Probably it won't matter anymore, right? This is already strong, so you go to here anyway. Then is this shape distractor still matter? It does not matter anymore. Okay. So originally, this is strong, this is weak. So I go here first, and then I go back here, so you have to capture. But if I'm looking for the strong one, then I go there already. Then I will not be affected by the weaker one. So you get this? So therefore, search priority based on stimulus saliency. Okay? Another evidence for stimulus triple attention. Okay, any questions? If not, so let's take a break. 好啊好啊。即係之前你講咗話做 attention 同埋飛鳥啦。係。咁我之前做即係做一啲文咧就有幾篇文都話 先？係啊，呢度咧報一報先啦。頭先即係講得唔係好清楚啊。嗱，呢一度咧呢個實驗咧，呢一度咧係個 target，OK。咁呢一度係講話邊一個字母係 target，所以呢度咧 P 係個 target，OK。咁所以個 task 要做咩咧？就係我一見到個 P 字咧，我就要撳掣㗎啦，最快撳。好啦，咁所以咧，其實就呢度有4個字母啦，1、2、3、4個字母啦，1、2、3、4個字母啦。是但無論係邊一個字母都好，總之一 P 咧，咁就 target 我就撳掣㗎啦，得唔得 ？OK。咁而喺呢一個實驗裏面咧，其實佢想去比較下，如果即係因為呢一個位同埋呢一個位都係一個新 item 啊嘛，咁佢就想睇下新 item 係咪特別搶眼啊？咁所以咧，佢就去比較一下，如果嗰個 target 咁啱得咁巧係新 item，會唔會快啲咧？咁而喺右邊呢個情況底下咧，個 target 咁啱得咁巧唔係新嗰個 item 嘅，咁又會唔會慢啲咧？咁樣得唔得 ？OK。咁就嗰個結果就係、如果個 target 其實1/4機會嘅啫。如果個 target1/4機會咁啱得咁巧係新嗰個 object 嘅話咧，咁係會快啲嘅。咁但係如果個 target 咁啱得咁巧唔係新 object 嘅話咧，其實都係1/4機會中啫嘛，但係咧就會慢啲嘅。OK， 咁就證明咗其實新 object 呢一回事係會令到你睇咗佢先咁樣。OK。係。即係 non-onset item 係舊嘅 item。onset 嘅意思就係新，non-onset 嘅意思就係舊。係啊。係啊。係。唔使反應。係，每一次都係啦，每一次都係。係啊，係啊，係啊。 咁我哋繼續。Okay. So just now we have saw experiment that shows the effect of top down and bottom up, or sometimes we say goal directed versus stimulus driven attentional control. So sometimes we look at a spatial location because we want to, so that's goal directed or top down attention. Sometimes we will attracted by some very salient, very eye catching stimulus, and we call that stimulus driven or bottom up attention. So this is actually related to the very famous, invisible gorilla experiment that you guys must have saw this before, right? 你哋都睇過㗎啦，係咪？呢條片。So I do not have to play it again. So let me first test your memory. Do you remember what do you need to do when you see this video? Count how many times the ball passed. Count which team. Count the white team, right? So count the white team. So if you count the black team, do you think you will be aware of the gorilla? Probably yes. So what kind of attention? Okay, just now we have learned top down and bottom up attention. Which one do you think is more relevant when I ask you, well, if you count the black team, then probably you will discover the gorilla? It's probably more related to top down, right? Yeah, we do not are aware of the gorilla because the task asks us to focus on the white team, and so the black color gone unattended, and therefore it's more difficult to find the gorilla. But if I ask you to count the ball passes by the black team, then very probably you will notice the gorilla. Why? Because the gorilla is black and you are attending the black color, right? So this is relevant to the top-down attention, right? Now, let's say if the gorilla do not dress in black nor dress in white, but if the gorilla dress in pink, do you think you will notice the gorilla? You should be able to notice the gorilla anyways. So what does it reflect? Bottom up, right? Bottom up attention. If everyone wear in black and white and you wear in pink, then of course everyone will notice you, whether you are a human or a gorilla or any kind of object, right? So this invisible gorilla, or more generally, inattentional blindness phenomenon, is due to a failure of both top-down and bottom-up attention, right? So you see how the inattentional blindness is explained by top-down and bottom-up attentional control. Okay, you see the relations between them. And what does it suggest? It suggests that without attention, do you still consciously aware of some visual stimulus? No. That means attention appears to be necessary for you to be aware of some visual object. Even you see that within your visual field. Okay? You may not be aware of that if you do not have the attention to that object. Right? When you are counting the ball passes, does this gorilla fall into your retina? Of course, yes. Retina, right? You're looking at this screen, you're counting the ball passes. Does this gorilla fall onto your retina? Of course, yes. Okay, it's within your visible visual field. But why don't you notice that? Not because these pixels do not fall into your retina, but because you did not pay attention to this object, to the gorilla. Most Etel 2001 turned this very interesting invisible gorilla experiment into a very boring lab experiment. But the structure is the same. Okay. But why should we do this? Why do we turn this very interesting experiment into this very boring format and discovering the same thing? It's because we want better control and we can manipulate some other variables we like. Okay. So let us first look at this task. This task basically is just the same as the gorilla experiment. So your task is to count the number of times white objects bounce off the edge. So these objects are all moving around the screen, and then you need to count how many times these white objects bounce off the edge. Okay? And then at some point, an unexpected object sneezes in. So this cross, for instance, okay, sneeze in and move across the scene. Okay, so this cross acts the same role as the gorilla, right? And you count the white objects, this is the same as counting the white team, right? So you can see this experiment is just the gorilla experiment in a very boring form. Now, however, the good thing is we can change factors, okay, in this experiment. Instead of attending to white, we can attend to black, right? Or instead of a black cross, we can have white cross, we can have a red cross. Okay, so we'll do this experiment. Okay, so most attempts have done this experiment and with other variations. So first, the condition that resembles the gorilla is this bar. Okay. So when the task was to attend to the white items and the unexpected object is in black, then how much can you detect it? 6%, very low. Okay, very low detection rate. That means if you are counting the white bouncing off edge, okay, similar to counting the white team passing the balls, you do not notice the black cross, which is very similar to you do not notice the black gorilla. Okay. However, in this experiment, they also do other color of the cross, for example, in gray or in white. And as you can see, the closer to your attended color, the higher the detection rate. So this demonstrates an effect of the top-down attention. Okay, but this time even more systematically. Okay. Or we may say, is this something to do with black? Black is dull. Nobody is interested in black. Maybe black itself have a problem. Okay. Then you can just reverse the experiment. Now what about counting the black? Okay. This time it is the black that get noticed, and the white get unnoticed. Right. So it's not an issue of white or black. It's an issue of attention. Okay. For your top-down attended color, you will always get a high detection rate. For your ignored color, you will always have a low detection rate. And it varies in degrees, okay, very systematically. Okay? So therefore, a top-down effect. But what about a red cross, a red unexpected object? Does it get detected? Yes. And is it attended? Okay, is it an attended color? It is not an attended color, right? You look for white or you look for black, red is irrelevant. Why would it get detected anyways? It's because it has a very eye-catching, very unique, okay, very salient color. Among all the other items, they are either black and white. You certainly get a red one, which is very eye-catching. Okay. So this reflects bottom-up attention, right? Therefore, when there is no goal-directed or stimulus-driven attention to the unexpected object, it goes unnoticed. These principles do not only apply to inattentional blindness, but also applies to change blindness. Okay. What is change blindness? So if I ask you to do a photo hunt game, where is the difference between the two? Okay. So we can spot out the difference. Right, this bunch of bush, right? This bush, in the same place, you do not have this bush on the left. Okay, so is it difficult to find? Easy, difficult, it's somewhat subjective. But when you try to find the difference, what do? You look around the picture, right? So let's just try another. Let's just try another one. Can you spot the difference? Yeah. Can you spot the difference? Yes, we can. So it's around here, right? Okay. Now, can we analyze it from the top-down, bottom-up perspective? Yeah. From the top-down point of view, is this leaves very important for us to take a look at? Probably not, right? Is it very eye-catching? No. So probably from the very beginning, we may not put all our attention here, right? From the very beginning, probably where we will pay attention to, for example, this house, which appears to be the main objects in this picture, right? So if the house disappears, probably we'll discover that, right? It's because we have top-down reason to attend to it, and it seems like attention is necessary for us to detect the change. Or if there is a okay, so now let me show you this way. Okay. If I show you something like this, okay, is the change very clear to you? Yes. Now, what is the difference between I doing this way and I show you by playing it? What is the difference? The difference is the intervening frame, right? It's the flash. So with the flash, it is much more difficult to detect the change. Without the flash, you can see the change almost instantly, right? So how can we make use of the top-down, bottom-up factors to explain this? When the frame is not intervening between the two, okay, what makes you find the difference? The sudden change, right? The onset and offset and onset and offset of the leaves is like the onset objects just now in Yantis and Janinis, right? The onset and offset itself, the motion signal, the change signal, okay, attracts your attention to go there. When your attention goes there, you can find out the change, right? So top-down and bottom-up factors, similar to the inattentional blindness, seems to affect how you allocate your attention. And it seems that attention helps you to do the task. There is one thing that is different between inattentional and change blindness. In attentional blindness, it is about whether you can see the object. But in change blindness, it is about whether you can detect the change. What is needed to detect a change? In addition to attention, what is needed to detect a change? How do you know there is a change? You first remember, okay, the object in the first scene, and then the intervening frame comes up, and then when the second frame comes up, you compare the object that you see with your memory, right? Because the first frame is disappeared already, so you need to rely on your memory to spot out any change. So when the video is playing and you're trying to find out the change, what you're doing is looking at each location and then wait for a change and then compare whether the same thing is saw in the same location that you're trying to attend. Therefore, change blindness not only have implication on how do you allocate attention, but also tell you that attention is needed to support the visual memory that is necessary for you to detect the change. Okay, so in attentional blindness, it shows you that attention is needed for awareness, right? In attentional blindness, it shows you that attention is needed for awareness. And similarly, in change blindness, it shows that attention is necessary for making an object that is originally visible to you to have a better memory. Okay, you need to attend there in order to keep that memory for later comparison. So with our attention, even you see that object, it is not enough because you need to keep that memory so that you can compare and to detect the change. So with our attention, therefore, we are subject to change blindness. We fail to notice that there is a change. In the illustration just now, when two pictures alternate continuously, the change generates a bottom-up signal that attracts attention. So this is what this is about the bottom-up attention that we have been mentioning. But when the pictures are separated by a blank screen, the motion signal is removed, and as such, we fail to detect any change unless we happen to attend to the change, okay, by chance. Just now we are talking about if an object is a main object in the scene, then probably we are able to detect it, even there is a frame in between. That's because if the changes are in the main object, then we have top-down reason to attend to that object, right? So therefore, the determinant of the change blindness, not only in terms of bottom-up attention, but also in terms of top-down attention, whether the change involves an important or an unimportant object. How do we define or how do we decide which object is important? Well, it's actually based on our experience, based on our knowledge, right? In this lion statue scene, if this statue disappears, probably we will notice it. But what makes we think that it is important is from our experience. We know that this kind of scene is the outdoor scene that shows a historical, statue. And then we know that this is the main character of the scene. And these two visitors may also be main character of the scene. So if there are any change about this, then probably we can detect it. Again, we know from our experience that this background are probably not very important, and therefore we overlook that bush, right? Therefore, according to Rensing, we combined some information to determine where to attend. Okay. Our knowledge, which include our knowledge about different scenes, and this is called the scene schema. But this knowledge is not sufficient. This knowledge is only knowledge. You have no relations to the picture. So you need to draw the relation to the picture. We include, okay, the layout and gist of the current scene. The gist refers to the general impression of the scene that help us to categorize the scene. Okay, and research shows that it takes a very short time for us to work out the gist of the scene. So in other words, we can categorize the scene from our impression very quickly. Is it a scene of a beach, or is it a scene of a room, or is it a scene of a visitor's place like the one just now? We can sort of categorize, identify this scene very quickly by our very brief impression or gist. Also, the layout of the scene gives us the location of the major objects. Okay? So we will combine this information. For example, if the current scene gives me an impression saying that this is a scene of a kitchen, okay, then from our knowledge about kitchens, we know that in kitchen, probably the most important thing are in the middle of the picture. All the utensils, all the tools are in the middle. And then we also know from our knowledge that on the top side of the picture, there may be some cupboards, and on the bottom, there probably is nothing interesting except the screen, right? Then we will make use of this knowledge to apply to what we have in the scene. For example, the layout of the scene is, okay, you really have some utensil and some cook looking towards in the middle, and then you have some couple on the top. And then you know that, well, the most important thing is probably in the middle, and for the bottom, nothing is important. Then perhaps there is something changed with the rubber screen on the ground, then probably you will not notice the change, right? So this is how we combine the three things. And Ransing proposed a way for us to understand the process. Okay. So this part refers to the visual processing. Okay, so nothing special. From the retina, okay, and then you identify some basic features, and then you form some objects. So this is the basic visual processing. Here is the cooperation between the top-down knowledge, scene schema, okay, or the knowledge about the scenes. We combine that with two information that come from the picture. The gist, telling you the type of the scene, the impression of the scene, and the layout, where are the important objects. Okay, and then with these three information, we can decide where to put our attention on. Right? For example, we know that this scene is what kind of scene, and which object is more important. Then we decide to focus on that object. Okay. Then let's say we focus on this area. Okay. So it's like attention is shining on this area. Okay. So with attention shining on here, okay, it will support the maintenance of the memory of the object. Okay, so here you can see this object actually. You can see this object visually. Okay. However, the problem is if your attention is not here, you see these objects, but after the flash and when you go to the other frame, these objects are not kept. Okay, until then, these objects are lost already. They are lost already. So these objects are not in the memory. Okay, when the second frame comes up. Okay, so even you see these objects in the first frame and in the second frame, you do not detect the change on these objects. Okay. However, if you have attention here, it helps you to generate a more stable memory representation for the object. Then, when the second frame comes up, you compare your memory with the new frame. Okay, then you can discover a change. Okay, so this is static, stable memory, stable object memory. And for this, you can see that, but when the flash comes up and then the second picture comes up, it goes away already. It is temporary. Okay. Temporary objects. Okay. Okay, so let's try once more. So where is the difference? Yeah, can you see this? Yeah, the engine. So if you cannot see that, if I do this, you will immediately see that, right? Okay, so again, okay, applying our knowledge, well, from this kind of a scene, we know that the main object is the airplane and probably some soldiers, right? And then the engine is probably not the most important object. Now, without the intermittent frame, we can see the change. But with the intermittent frame, we do not have the onset offset because the whole picture is onset and offsetting, right? So therefore, okay, we have no top down and bottom up attention to go here. Therefore, okay, not until I tell you it is here and then you allocate the attention here, okay, not until then you will not discover the change. Okay. Okay, so next topic. In the visual attention studies that we have been talking about, we used to assume that attention always has one focus. Okay, so we say if you attend here, you attend there. Okay, so it is like we always assume attention having one focus only. But is it the case? It is the next question. Okay, so imagine, okay, you are bringing your dog to the park, and then you release the dog to run around the park. Then of course you do not want to lose your dog, so you will well keep following, okay, looking after your dog, and you visually track your dog when the dog is playing around. So this is one focus of attention, right? You keep focusing and tracking where the dog runs. Now, suppose you have two dogs, okay? The two dogs are running around, okay? Do you have two attentional focus, okay, to track each dogs, okay? So this is the question, okay? Do you have two attentional focuses, or we call them foci, okay? That means focuses. Do we have two focuses to track each dog independently? We do not know, so we need to do a study. So O and Peschler 2000 have done an experiment. So usually we ask people to detect one target, and then we assume one attention is like covering these objects. Okay. Now, what about two objects? If I queue two locations and the people are to detect two objects, okay, then what will happen? Will you have only one attentional focus and you use a bigger attentional focus to cover both? Or, okay, you have two objects and then you split your attention into two, okay, then you will cover each object by one attentional focus. Okay, and in total you have two attentional foci. Okay, which will be the case? To test this difference, okay, you need a condition that will generate different predictions from each hypothesis, right? We always do experiment like this. To answer a question, we have two possible answers. We try to find out a condition that each answer will produce a different outcome, right? Now here, their rationale would be, if I ask you to respond to a middle object, okay, when attention is one, okay, you have no choice but also to focus on the middle region. Then when you detect this middle object, will attention benefit this object? Yes. However, if attention can be split into multiple foci, then will attention benefit this object? No. No, or less actually, right? So this is the experiment that they've run. So we usually, in this kind of attentional studies, we usually have one cue, and then attention will go to that cue, because that cue is usually helpful. This time, you have two cues, okay? So what will happen? So you have two cues. Both cues are usually useful, so attention will cover both cues. Well, we do not know whether attention will cover each cues independently, or it will cover the entire region if attention is 1. Okay? So we do not know. And then, for the Q to be useful, usually the target numbers here, the target digits, will be at the same place as the Q. So in 80% of the case, these two Qs are helpful. So the number that you are going to report will at the same place as the Q. Okay? But the most interesting part, of course, is in the minority. Okay, in the 20% of the invalid trial. So here, the target would be in the middle position and in another position. Okay, so we are more interested in that when in the middle position. Okay, what would happen? If attention is 2 or can be split, then attention may be split over this A and W position, this left or right position, right? However, if attention is 1, it may cover the entire location, and then 5 would get benefit. Okay, so we can see whether 5 receive any benefit or not. Okay, to decide whether attention can be split or attention is 1. So let's look at the results. So according to the results, when the target is left or right, that means valid, of course, the performance is the best. What is the performance? Accuracy. Okay, so the performance, of course, is the best when the Q is valid. When the target is far, that means this one, okay, then of course performance cannot be good because attention is not here. So of course, poorest performance. The most important part is the middle location. If attention also cover 5, if attention also cover the middle position, should it be any poorer than the left or right location? No, it should be equally good. However, it is much poorer, right? It is much poorer. That means the coverage of attention does not go to the middle space. Okay, the coverage of location does not go to the middle space. That means attention can be split. So results, high accuracy at Q location, left and right, reduced accuracy at the middle position. If attention is 1, then it should benefit the middle position. However, the middle position do not get a lot of benefit. That means multiple attentional foci. Okay? In the last lecture, we have discussed object-based attention already, right? So probably we can go through them very easily because we have already known. So when we attend, okay, we ask, we used to say we attend to locations. Yeah, possibly we attend to locations. But we will also ask, do we attend to objects as a whole? Do we take unit? Do we take objects as the unit? So if we attend to objects, if we attend to this marker, okay, then it should take no time for you to, okay, for you to look at the cap and for you to look at the end of the marker. Why? Because you're attending to the whole marker. Then attending to the cap and attending to the cap to the end, it should take no time for you to switch your attention because you didn't switch your attention. You're attending to the whole objects. So if we attend to whole objects, it should take no time to shift attention within objects. However, if attention is location-based, then it should take time whenever you move across space. Okay? So when you focus on the cap and then you move your attention to the end, then you're moving across space. Then, if attention is location-based, it should take some time. Well, when it takes time, then we have already talked about this two rectangle paradigm, right? So attention will go here to the Q because the Q is usually useful. Therefore, attention is here, 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 and also here. Right? So if the target occurs at the location where attention goes, then it is the valid condition. Of course, this will give the fastest performance. If attention covers the whole object, then it should not take time to move here, right? However, if it takes time to move here, this will reflect location-based attention. On the other hand, if it takes time to move from the acute location to the different object location, it also reflects location-based attention, isn't it? But if there is anything more, okay, between this condition than the last one, then that additional cost is a different object cost, or it reflects the same object advantage. So what do we have? We remember that this y-axis, okay, tells you how much slower the invalid condition are as compared to the valid condition. Okay, we know that the valid condition is going to be the fastest, so we take it as the baseline and to see how much slower each condition, right? So in the second condition here, invalid same object, it produces a cost. Okay, so relative to the valid condition, it is 35 milliseconds slower. That means it takes time to shift attention even within an object. That means we have evidence for location-based attention. Okay. However, to shift attention across the same distance but across different objects, it takes even more time. Therefore, it takes a longer time to shift attention across objects, even the distance, the spatial distance is controlled. Therefore, we also have evidence for location-based attention. Okay, so in this Eckley driver Ruffle 1994 experiment, it gives evidence for both a spatial and object-based component in attention. Okay, so very quick revision on this experiment. If you remember in the last lecture, the other approach to study object-based attention is by using an overlapping stimuli, right? So the study that we have looked at the Duncan experiment, the overlapping object experiment, is well, you can see is the original one. Okay. Then there are other studies that takes this paradigm. So O'Craven dynamic chemistry is one of those. Okay. So it makes use of overlapping stimuli, and the logic, we are familiar with the logic. The logic is if two objects overlaps, then you cannot select only one of them on the basis of spatial location, right? If you select on the basis of location, and then if you select that location, you always end up selecting the other one, right? Because it's also occupied that location. So if you can select one of them, then that means you have object-based attention. You have object-specific attention, right? Okay. So here you have two overlapping objects. So unlike the one in Duncan, okay, actually use semi-transparency to overlap two objects. So as you can see, it's a face and a house. Okay. So in O'Craven study, they ask participants to either focus on the face or to focus on the house, and then they measure the fMRI signals. Okay, recorded from FFA. We know the FFA will respond to face, and also recorded from the PPA, the parahippocampal area, and we know that this PPA will respond to house stimuli. Okay, so by measuring fMRI, they want to know whether we have object-based attention. Well, to make a guess, if we can attend to face, okay, then that means when we are actually really attending to face, then FFA probably will have stronger activation, right? And then PPA probably will have poorer activation. However, if we do not actually have object-based attention and there is only spatial attention, then whenever we look at this location, we can see both of them, right? Then both should be get activated equally. Okay. However, in this experiment, they do a very little twist to the experiment. So they do not directly ask them to focus on the face or the house. Instead, one of the object here will move, and then they will ask the participant to attend to the moving object or to attend to the static object. Okay, so it's a twist. But well, effectively, they are asking people to focus on the face or the house. Okay. So this is the results, which is a little bit difficult to see. So we want some, um, we want to mark it so that we can see it better. Now, first, okay, we have 1, 2, 3, 4, 5, 6, 7, 8 points here. Okay, so let us mark all of them. So first, which data point refers to attending to face? Okay, let's say we use yellow to represent attending to face. Okay, so which one is attending to face? If face is moving and we are attending to moving, then that means we are attending to face. Okay, do you get it? Okay, if the house is moving, that means the face is not moving. Then attend static is attending to face. Okay? And then, again, if the face is moving and if we are attending to the moving object, that means we are attending to the face. Okay? And then, if the house is moving, but then we attend to the non-moving object, the static object, then the static one is face. Okay, do you follow this? Okay? And then in a very similar fashion, if the face is moving but we attend static, that means it is a house. If the house is moving and then we attend to the moving object, then that means we are attending to the house. And so on, and so on. So you follow this? Okay, so now it is much clearer. Okay, when we attend to the face, FFA have a stronger activity, right? Than when we attend to the house. And when we attend to the house, PPA shows a stronger activity than when we attend to the face. Okay? So the result is quite clear, right? When we attend to face, FFA activate. When we attend the house, PPA activate. So does it mean we are able to attend specifically to the face or the house? Yes, we can. What would happen if we can't? They will be the same, right? What would happen if we can't attend specifically to the face and not house? Or we can't focus specifically on the house but not face? Okay, what happens when we can't do that? Okay, when we do not have object-based attention, then when we look at that screen, we simultaneously process both face and house, right? Then will you still see this difference? No, we won't. Okay? 清唔清楚？得唔得？ Therefore, we find evidence for object-based attention. Okay? All right. Okay, Emma. Okay, so just a moment. 咁跟住咧就嗱我就唔逐點咁講啦嚇。咁我負責做 負責做 experiment 嗰個咧，咁就自己即係睇緊啲啦。OK。咁我大概講下啦。咁咧做 experiment 嗰個咧，咁就早少少去，即其實你係自己夾嘅啫，冇話早唔早少少。咁咧就要首先 download 呢一個zip file 啦。如果譬如話我講 face 先啦，咁就 download face 呢個，咁就 save 低佢啦。咁咧，跟住咧就 extract 咗佢啦，加速咗佢啦。跟住咧入邊咧就其實就係如果你唔夠 consent form 去 instruction， 即係 instruction 你其實需要 fill 一份嘅啫，你唔夠 instruction form 都唔會唔夠 consent form。不過總之佢就喺度啦。咁如果你唔見咗，可以睇到啦。咁個 folder 裏面咧就係嗰個實驗嘅程式。咁咧實驗開始之前咧，你就試下機先啦，咪做下就壞咗，咁就唔好啦。咁首先咧就會打 subject number 落去。咁如果係試下嘅時候咧，咁就0啦。因為咧由1開始嘅真正嘅 subject number，咁如果你要試下可以打0。佢係黐緊線嘅，因為咧冇講錯，我話黐緊嘅，係一個現在進行式啫。因為點解咧？因為咧呢一 part 咧係唔可以錄影嘅，係啦，所以咧佢會黐線，我 stop 咗佢先。